So today we are diving to concurrent assertions examples for processor and memory interface. So let's get started. So as we can see in the question, it says write the following assertions for the following processor memory interface signals. And let's go through the signals. So here we have an 8-bit address bus which takes input from the processor side, and here we have an 8-bit data bus which is bidirectional for both the read and write operations. And here we have some 1-bit input signals from the processor. So when start is asserted during the start of a transaction, and in the very next cycle the read is asserted, and if it is deasserted then it is a write transaction, if it is asserted then it's a read transaction. And then we have other signals like reset and clock. Then we have other some signals, some single bit bidirectional signals including data valid and finish, which indicates that a transaction is complete. So here's our first assertion. It says the address line are valid for the cycle in which start is asserted and the following cycle. So let's begin with the property. So for this case, I will be using the overlapping implication operator to indicate that the address is stable in the same cycle when start is asserted. And since it should also remain asserted on the next cycle, I will be using a consecutive repetition of 2. I will use $is unknown. So here's the consecutive repetition of 2. I will assert the property. So we are done with this property. So let's move on to our next assertion. It says when data valid is asserted, the data lines should hold valid data. And it's a very simple one. Let's name this valid data underscore property. Let's write the non-overlapping implication operator. Oh, I mean the overlapping implication operator. $is unknown. And data. Let's assert the property and name the property. I mean name the assertion. Okay, I didn't use @posthclock here. Anyways, I can use it right here. It's the same thing. So in our next assertion, the start, read, and data valid should be asserted for only one clock cycle. So for this particular cases, I will be using non-overlapping implication operators, and let's do it. So this indicates that the start will remain asserted for only one clock cycle. Then on the next clock cycle, it should be deasserted. Otherwise, the assertion or the property will fail. Let's move on with the read signal. Okay, so next is the data valid signal. Let's assert the last property. So we are done here. So here we can see it says that a read transaction should complete in 2 to 10 cycles and a write transaction should complete in 2 to 7 cycles. So the complete transaction begins with the start asserted, followed by a read signal asserted or deasserted, which depends whether it is a read operation or a write one. And it is then followed by the finish signal, which indicates that the transaction is complete. So let's begin. So I will be using the non-overlapping implication operator here. So when the read is asserted, indicating that it's a read operation, then I will wait for finish, which indicates that the transaction is complete. So note here that I am writing the range of 1 to 9 because we started counting the cycles when the start is asserted. And so let's write the same thing for the write transaction. So for the write transaction to begin, the read should be de-asserted. So since it says that it should be in the next 2 to 7 cycles, I will write the range of 1 to 6. And it finishes when the finish is asserted. So note here, I am not using the logical or, which you will see like this, and it is because it can only be used with expression and it requires both the LHS and the RHS to be evaluated in the same clock cycle, which is not happening here. So let's assert the property. And we are done. So in the next one, we can see that it says then the start signal should only be asserted once during a read or write transaction. So let us begin with the property. So I will write it as no double start. And I will be using the non-overlapping implication operator. So in the very next cycle, the start should be deasserted, and I will be using throughout. So it will remain deasserted throughout when the transaction is not finished. So here we are using the goto repetition operator to indicate that the finish is required to be asserted for only once and any time after the start is deasserted. So the condition is very simple. It should remain deasserted whenever it sees the transition of finish. So moving on with our last property, which says that no finish for start, but it doesn't matter if the reset. So basically it means that when finish is asserted, indicating the transaction is complete, it should remain deasserted until unless it sees another start signal asserted. So, and it also mentioned that it doesn't matter if it has a reset signal, if the reset signal is asserted. So let's begin with our property. I will name this no finish before start, and I will write disable if and only the reset is asserted. Then I will write the property. Now, when the finish is asserted, then on the very next cycle, the finish should remain deasserted until unless it says start. I will write the assertion check. Okay, I again forgot to write the posage of clock, but I will write it right here. So this is the event in which the property will be checked. So here it is. We are done. I hope you find this video useful. Thank you so much. Wait, there's a one correction. It should be throughout, not through. Alright, thank you so much.